Hello everyone, my name is Zixing, and I would like to thank the organizers for giving me the opportunity to tell you about private-key quantum cryptography with boson sampling devices. So here is a roadmap for where we're headed. Firstly, I will introduce boson sampling, then I'll discuss our protocol, and then I'll tell you about quantum data locking, which is at the heart of our protocol, and then I'll give you a sketch of the security proof. Okay, so what is boson sampling? Since the conception of this term, it has attracted a lot of attention both theoretically and experimentally. Well, boson sampling is a non-universal model of quantum computation where the task is this. You have a n single photon Fock state input into an m-mode interferometer, and the task is to sample from the output. Now, it has been shown that the output photon distribution is proportional to the permanent of the n by n submatrix of U corresponding to where the input is. Now, if the unitary U is chosen from the Haar distribution and m is much larger than n, that is, we have many more modes than the number of photons, then Aronson and Arkhipov show that the submatrix approximates that of a random matrix, and in this case, calculating the permanent is known to be sharply hard. So this means that it scales exponentially on a classical computer, which is why we think that boson sampling is post-classical. To give you some intuition as to why the output is proportional to the permanent, well, if you have a photon input at mode I, it transforms like this. Say we have a photon input at modes 1 and 2, the probability that they will come out at modes 2 and 3 are given by the amplitude of them both going straight through and that and added of them crossing over. And this probability amplitude is proportional to that particular submatrix permanent. Okay, so boson sampling was the first time that we have proof that quantum computers may have an exponential advantage over the classical counterpart. And just about every large photonics group has been trying to implement an experiment, and I believe to date, Jianwei Pan's group holds the record of using 20 photons in 60 modes. Okay, so we know that at the output of a boson sampling device, the quantum state has a large photon number path entanglement, which makes it hard to crack classically. But what about by a quantum computer? And there are a few boson sampling inspired applications for quantum metrology and quantum chemistry. But as far as we know, we are the first to make use of the actual original protocol. So here we have an information theoretic proof that boson sampling is useful for cryptography. And by useful, I mean that we can either do efficient quantum key distribution or we can encrypt a message that's much longer than the key. And the latter is what we will focus on. And then we move out of the no collision regime, so the no photon bunching regime, and we show that this actually leads to a very efficient scaling of the encoding Hilbert space. So we have something like the quantum Enigma machine. And I'll tell you about the Enigma machine now. So what is an Enigma machine? Well, it was a device that was used extensively by Germany during the Second World War. So it was an encryption device because at the time they know that any signal that they transmit over the radio would be intercepted by the Allies, so they will need to encrypt the message. Now the Enigma machine looks like this. It works essentially by substitution, where you're swapping letters of the alphabet. So for example, you would swap A for L, B for U, etc. And this would correspond to a setting on the machine. So you type in your plain text, ciphertext comes out, you transmit the ciphertext, and on the other side, someone else has a copy of the machine, you type in the ciphertext, and the plain text comes out. And if you don't know what the substitution is, then the message becomes very time-wise expensive to break. Well, that is for the technology of the time. This is, of course, breakable by using a brute force method. On the other hand, if the message is encoded at quantum state, one big advantage we have on our side is the known cloning theorem. So you get basically one shot at measuring the message, and that's it. Okay, so now we are ready to talk about our protocol. So here, Alice and Bob are the two legitimate communicating parties, and Alice wants to send a message to Bob. So Alice can choose her code words psi of x from the m choose n possible configurations of input photons. So she's using n photons, and there are m choose n possible ways of distributing them at the input. And each quantum state that she transmits m choose log, the log of m choose n bits. Okay, so Alice and Bob pre-share a k-bit unconditionally secure secret key. In advance, but not necessarily in secret, Alice and Bob agree upon a set of k random m by m unitary matrices, UK. So here, after the state preparation of psi of x, that is at this point, Alice applies the unitary UK associated with the key, and then she sends this state to Bob. Upon receiving the state, Bob decrypts using UK dagger, and then he measures the state at the output by photon counting. Now, if Alice has applied UK and Bob has applied UK inverse, then this block turns into the unitary, and Bob measures what Alice has input. And our goal is to show that Eve indeed cannot read the message. I'll show you the result first. So we're defining a net secure communication rate as log m, which is the number of bits that we transmit securely, minus the number of bits used for the encryption. So log m is given by the blue solid curve there, and log k is plotted at the bottom for different security parameters. And this is for in this Boson sampling regime where we have n much larger than n. As we see, we have a potentially exponential gap between the length of the message transmitted and the number of bits used in the encryption. So now I have to tell you the framework under which our results were derived and how it relates to boson sampling. So the technical results from Aronson and Arkhipov were crucial in calculating the key consumption, so the number of encryption unitaries needed, but the classical computational complexity of boson sampling is not required. And this is a strength of our protocol because we simply don't need this assumption. And then we go beyond the boson sampling regime and show that the scheme actually works for any number of photons and modes. Here, we're using the accessible information as the security quantifier, under which the quantum data locking effect kicks in, which I'll tell you about shortly. But in order to use the accessible information, we do have to impose the bounded storage model, where we assume that Eve has bounded quantum memories in time. So here we have to say that Eve has quantum memory, but she can only store them for a limited known time, just so that at some point she has to make a measurement. And then and then and then Alice and Bob can do the post-processing. Okay, so a quick reminder for what the mutual information is. So in classical information theory, if X is a random variable with potentially m outcomes, each occurring with probability P of X, then the Shannon entropy of X is given by this expression over here, where we have the negative of the summation of P of X times the log 2 of P of X. This measures the amount of information one gets by measuring the outcome. So now, if there are now two variables, then the mutual information between A and B is HA plus HB minus HA joint with HB. So it measures the degree of correlation between these three variables. So HA, for example, can be from Alice's source encoding, and HB could be either Bob's variable or Eve's variable. So if these two are communicating parties, legitimate communicating parties, we want I of AB to be big, but if HB belongs to Eve, then we want I of AB to be small. And the accessible information is simply the maximization of the mutual information over all the possible measurements. Okay, so now we are ready to talk about the quantum data lopping effect. So when Alice sends the state to Bob, Bob sees this state over here because he has access to the secret key. So this is summing over all the possible messages Alice can send. And in our notation, we write this as the mutual information of Alice's variable, X, and Bob's variable, Y, and K, which is the number of the K, which corresponds to the variable of the secret key. And this is equal to log 2m in our definition. On the other hand, if Eve was to intercept the state, then she sees this following. We see that she sees the state which is averaged over all the possible encryption unitaries, summing from 1 to k, and we don't know what this mutual information is yet. Now, if all the quantities are classical, then there is this inequality here which dictates that the difference between the mutual information, these two mutual informations, so the mutual information between Alice and Bob and Alice and Eve is lower bounded by log 2 of k, which is equivalent to the one-time pad that if you have a key that is log k bits long, you cannot hide a message just longer than log k bits, and this is a well-known result. On the other hand, there's a striking difference in the quantum regime, where you have if you are encoding the message in a quantum state, that the accessible information between Alice and Bob and Alice and Eve can be much, much bigger than the number of encryption unitaries. So this is something that's uniquely quantum and has no classical counterpart. Okay, and now we're ready to go into the security proof. So our goal here is to upper bound the accessible information between Alice and Eve with high probability. So we want to upper bound this accessible information to within 2 times epsilon times log m, where epsilon is a security quantifier that we can choose to be arbitrarily small. And once again, the accessible information for Eve is given by this expression over here, where Eve can maximize this over her measurement basis, or her choice of measurement. So Bob sees this particular state from Alice, as we've seen before, and Eve sees this particular state from Alice that we also have seen before. So the starting point is that quantum mechanics dictates that Eve's measurement takes the form of a set of PLVM elements, which looks like this. And if you sum over y, then you end up with the identity operator. So when you apply equation 11 to equation 10, Eve's mutual information looks like this. So there are two terms in here which we will bound separately. So we're going to bound the first term using the matrix channel bound and the second term using the Maurer bound. And we will look at the matrix channel bound now. So the matrix channel bound states that if you have a collection of permission matrix valued random variables, which has mean value mu times identity, then the probability when you add up a bunch of these and that the sum deviates from the mean is exponentially suppressed. So it is exponentially suppressed in terms of the number of elements that you add, which is t, as well as the sum. So if we apply this to the first term, we show that the first term is less than 1 times epsilon multiplied by the mean state, in which case, for us, it's a maximally mixed state. So we actually have to use a slightly more complicated version of the matrix channel bound in order to account for photon bunching, but I won't show you that here. And for the second term, we apply the Maurer tail bound to show that this particular quantity here is larger than 1 minus epsilon of that when you measure the maximally mixed state. So very similar to the matrix channel bound, except this time the tail bound applies to random numbers. So it's saying that when you add up a bunch of random numbers, the probability that is smaller than 1 minus tau of the mean is exponentially suppressed. So one important quantity over here is gamma, which is the ratio of the second moment of the random variable divided by the random variable squared, because this actually dictates the number of encryption unitaries needed for the key, for the message per round of the protocol. And gamma here is also where we need to do a maximization have we had to account for photon bunching. Okay, and gamma actually is also where our protocol ties in with boson sampling. So in order to calculate gamma, the quantity we want to calculate is the overlap of a generic vector phi with the encryption unitary applied to the quantum state. And in the boson sampling regime, this is proportional to the absolute value squared of the permanent, which we can calculate. The other quantity that we need is the second moment or the fourth moment of the permanent, which we extract from the Scott Aronson paper. And here we found that gamma is upper bounded by 2 times n plus 1. And to complete the security proof, we account for photon bunching by modifying gamma, and then we extend this to all the possible code words X. We extend this to all the vectors that Eve can use. And when we put this together, we end up upper bounding Eve's mutual information to within 2 times log epsilon times log m. And this result holds provided that the number of encryption unitaries is larger than gamma times the dimension of the Hilbert space divided by m, because the n photon Hilbert space is actually slightly larger than our encoding space, and another term that's proportional to log 1 over epsilon. Okay, so the probability of failure of our protocol is given by this complicated expression over here, but the good news is that everything sits inside exponentials, so we can make them disappear if we make k large enough, which corresponds to this complicated expression. And when we take the log of k corresponding the number of bits that we need, it collapses to this expression that we've seen before. Okay, so you might ask, so it's all well and good to think about a noiseless channel with infinitely many photons and modes, but does our protocol still work in the limit of having a moderate number of photons and modes? And does it still work in the presence of loss? And the answer is yes. So in this particular figure, we're showing 20 modes and 4 photons, and with some losses. So the purple there is for a perfect transmission, and we have the green 90%, red 70%, and the blue 50%. So we can tolerate a moderate amount of loss and still obtain a positive key rate. And then the referee asked, so how does it compare to BB84? Well, I'm really glad they asked, because that question gave us our money shot. So here we are looking at the information density per mode. So let's talk about BB84 first. BB84 can transmit at most 0.5 bits per mode, even if you use a bias basis choice, because you use 2 modes, right? And then so per round of the protocol, you transmit 1 bit of information, and you're using 2 modes. Whereas for us, our encoding space is of size m choose n, and log m choose n divided by m can be larger than 0.5 because you're allowing the photon to take all possible lanes. Now, so here we're looking at the number bits per mode transmitted as a function of the transmission parameter, so the loss parameter. It only makes sense to compare our scheme to the BB84 in direct reconciliation, because our scheme is a direct reconciliation one. So which means that we are encrypting all the information at Alice's point, at Alice's end. So here is BB84 in red, and our protocol using 20 modes in green, and our protocol using 40 modes in blue. And we optimize over the number of photons at the input, because there's a trade-off between the number of bits needed for the encryption and the information density, of course. And we have to note that we use strictly less photon than m divided by 2 as per BB84. Now we see that our protocol for m equals 40 already does better than BB84 for all levels of the transmission parameter. And we expect the curve to do something similar when we go to reverse reconciliation. Okay. Now, in conclusion, we have a quantum private key encryption protocol, which is the first actual application of boson sampling. We have an information theoretic proof that our protocol works for any number of modes and number of photons. And in the future, we would like to remove this need to impose the bounded quantum storage model. We might look at scattershot boson sampling or weak coherent states, because they're slightly easier to make in the lab. We will look at error correcting codes, privacy amplification, and time binary coding for long distance communication. And giving credit where it's due, the idea was first conceived by, I guess, John Dowling and Peter Rode somewhere in Sydney a couple of years ago, but we have no idea how to do the security proof until Cosmo Lupo came along. I would like to thank Professor John Dowling for his encouragement for the years I've known him, and he was really like a father figure to a number of us on the paper, actually. So the quote on the slide over there, I'll give some context. So John told the story of how when Yang and Lee were doing their experiments and writing papers, they would alternate between who would be the first author. And when they completed the symmetry breaking experiment, they knew that this was going to lead to a Nobel Prize. So one of them went to the other and said, I know this is your turn to be the first author, but I want it to be me this time. And apparently they never spoke to each other again, apart from shaking hands at the Nobel Prize ceremony. And that particular quote there followed. So thank you for your attention, and I'll take any questions.